Introduction. Today, two friends, Roy and Sid, came on a beachside for picnic and they both are enjoying very well. This beach is full of nature and I like this kind of landscape so much. Roy, see the high sea waves there. Looking so glorious, don't you think? Yeah, it's amazing. But do you know, these sea waves follow which phenomenon? No. Can you please tell me? Yeah, sure. The sea waves follow oscillations. They repeat their motion periodically. Okay, I got it. I want to know more about it. Can you tell me? Of course I will. Students, in this lesson, we will learn about oscillation. Periodic and oscillatory motions. Periodic motion. It is that motion which repeats itself after equal intervals of time. The interval of time is called the time period of periodic motion. Some examples are motions of planets around the sun, rotation of Earth about its polar axis, motion of the hands of a clock. Oscillatory motion. If a body moves back and forth repeatedly about a mean position, it is said to possess oscillatory motion. Some examples are motion of the pendulum or a wall clock, oscillation of a mass suspended from a spring, motion of swinging. Simple harmonic motion. Simple harmonic motion is a periodic to and fro motion in a straight line about a mean position in which acceleration is proportional to displacement and is always directed towards the mean position. Consider a particle oscillating back and forth about the origin of an x-axis between the limits plus a and minus a. It is simple harmonic motion if the displacement x of the particle from the origin varies with the time as xt is equal to a cos omega t plus phi, where a is equal to amplitude, omega is equal to angular frequency, phi is equal to phase constant. In simple harmonic motion, displacement is a sinusoidal function of time. Velocity and acceleration in simple harmonic motion. The speed of a particle v in uniform circular motion is its angular speed omega times the radius of the circle a. V is equal to omega a. The direction of velocity v at time t is along the tangent to the circle at the point where the particle is located at that instant. The velocity of projection particle is given by vt is equal to minus omega a sine omega t plus phi, where negative sign shows that vt has a direction opposite to the positive direction of x-axis. Instantaneous acceleration of a particle undergoing simple harmonic motion can be determined by the method of reference circle. The centripetal acceleration of a particle p in uniform circular motion has a magnitude of v square by a or omega square a, and it is directed towards the center, that is, the direction is along PO. The instantaneous acceleration of the projection particle p dash is given by at is equal to minus omega square a cos omega t plus phi is equal to minus omega square xt. Example. Let us take an example of velocity and acceleration in simple harmonic motion. For a simple harmonic motion with amplitude 3 cm and time period 5 seconds, find the velocity and acceleration at equilibrium position and displacement of 2 cm from equilibrium position. Let us see the solution. Here, amplitude A is equal to 3 cm and angular frequency omega is equal to 2 pi upon t is equal to 2 pi upon 5 radian per second. The expressions for velocity and acceleration in terms of displacement are v is equal to omega under root of a square minus y square and a is equal to omega square y. At midpoint y is equal to 0. Hence, v is equal to omega a is equal to 3.77 centimeter per second and A is equal to 0. At y is equal to 2 centimeter we get V is equal to 2 pi under root 5 upon 5 is equal to 2.81 centimeter per second. A is equal to omega square y is equal to 2 pi upon 5 whole square into 2 is equal to 3.16 centimeter per second square. Force law for simple harmonic motion. To calculate the force acting on a particle of mass m in simple harmonic motion, we are using Newton's second law of motion and the expression for acceleration of a particle undergoing simple harmonic motion. Ft is equal to ma. Putting value of a, we get Ft is equal to minus m omega square into t. Ft is equal to minus k into t. Here, k is equal to m omega square. Omega is equal to under root k upon m. Force is always directed towards the mean position. Hence, it is sometimes called the restoring force in simple harmonic motion. The force is linearly proportional to xt. A particle oscillating under such a force is called linear harmonic oscillator. Energy in simple harmonic motion. Kinetic energy. Velocity of a particle executing simple harmonic motion is a periodic function of time. It is 0 at the extreme positions of displacement. Kinetic energy is given by K is equal to half mv square is equal to half m omega square a square sine square omega t plus phi is equal to half ka square sine square omega t plus phi. It is also a periodic function of time, being 0 when the displacement is maximum and maximum when the particle is at the mean position. Potential energy. The spring force F is equal to minus kx is a conservative force with associated potential energy. U is equal to half kx square. Hence, the potential energy of a particle executing simple harmonic motion is Ux is equal to half kx square is equal to half ka square cos square omega t plus phi. Thus, the potential energy of a particle executing simple harmonic motion is also periodic, with period t by 2 being 0 at the mean position and maximum at the extreme displacements. Total energy. Total energy of this system is E is equal to U plus K is equal to half K A square sine square omega t plus phi plus half K A square cos square omega t plus phi is equal to half K A square. Hence, the total mechanical energy of a harmonic oscillator is independent of time. Resonance. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance. Let us understand with an example. 5 simple pendulums of different lengths are suspended from a common rope. The pendulums 1 and 4 have the same lengths and the others have different lengths. Now, let us set pendulum 1 into motion. The energy from this pendulum gets transferred to other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which pendulum 1 oscillates. The response of pendulums 2, 3 and 5 are: they first start oscillating with their natural frequencies of oscillations and different amplitudes, but this motion is gradually damped and not sustained. The response of pendulum 4 is in contrast to this set of pendulums. It oscillates with the same frequency as that of pendulum 1 and its amplitude gradually picks up and becomes very large. A resonance-like response is seen. Did you know? The potential energy is minimum at midpoint of motion and at maximum displacement the potential energy is maximum. The rise and fall in sea level is because of tidal forces and the tidal current that is created is an oscillating moment. In 1656, the Dutch scientist Christian Huygens built the first pendulum clock. This was great improvement over existing mechanical clocks. Their best accuracy was increased from around 15 minutes deviation a day to around 15 seconds a day. Summary. Let us summarize what we have learned. The motion which repeats itself after equal intervals of time is called the periodic motion. If a body moves back and forth repeatedly about a mean position, it is said to possess oscillatory motion. The number of cycles completed in 1 second is called the frequency of oscillation. The change with time of any physical property under consideration is called displacement. Simple harmonic motion is a periodic to and fro motion in a straight line about a mean position in which acceleration is proportional to displacement and is always directed towards the mean position. The total mechanical energy of a harmonic oscillator is independent of time. When a simple pendulum is released, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance.